Hey everyone, today we're going to talk about cylindrical and spherical coordinates, introducing a new way to represent different regions and functions that we are going to work with and hopefully make them a little bit easier to integrate and do other types of operations with. Before we jump into cylindrical and spherical coordinates, I kind of want to start with a little bit of a warm-up of working with polar coordinates, which should hopefully be somewhat familiar to most of you, either from like Calc 1 or Trig or something like that. So for that, first we'll look at the identities for polar coordinates, do a couple of examples, and then we'll really launch into the cylindrical and spherical coordinate stuff. All right. So for polar coordinates, we have the following identities. We say our goal is to go from working in Cartesian coordinates x, y, into working with everything in terms of an r and a theta, where if we look at our graph, r is kind of like, if we have a point x, y, we can talk about it in terms of distance from the origin r, and then an angle theta that tells us how far that arm moved. And so in order to be able to get r and theta from our information of x and y, well, I mean, you just use the Pythagorean theorem here. R squared is equal to the x squared plus y squared. And then a little bit of trig tells you that theta is equal to inverse tangent of x over y. And the other piece of information that we have, though, if we wanted to kind of go the opposite direction, or be able to make swap out for like things that are in x and y, if we're looking at the function itself, x is going to be equal to r cosine theta, because it's this adjacent part of this kind of triangle right here, and then y is equal to r sine theta, because y is really just the length of that vertical leg there. Okay, so again, hopefully that should all be familiar to you, and we're just going to apply this with some whole regions instead of working with individual points or functions. Okay, so for example, we can convert a region D that is equal to the set of all points x, y, such that, let's say that x is greater than or equal to 0, and x squared plus y squared is less than or equal to 4. Here's into polar coordinates. So first and foremost, I like to be able to draw pictures, as I've said before. So let's just get an idea of what this region looks like. This x squared plus y squared less than or equal to 4 is actually going to be like the inside of a circle, and that circle is going to have radius 2. So we're going to be looking at a shape that's kind of like this, and we want the inside of it, like so. Okay. So, and the reason that I know I only want this half here is because we're told specifically that x is greater than or equal to 0. So we're only looking at this half of the circle. All right, so now we want to get this expression, convert this expression for the region into polar coordinates. Well, the first thing we note is that we have this x squared and y squared, and that's less than or equal to 4. Well, if we go back to our conversion, x squared plus y squared is equal to r squared. So x squared plus y squared less than or equal to 4 converts into r squared is less than or equal to 4, which means that we really want r to be less than or equal to 2. And I also want to point out that r is always going to be positive because it's really just the distance. It's the how far away you are from the origin. Which direction is pointing is really just dependent on theta. So r is always also going to be greater than or equal to 0. This has nothing to do with the fact that x is greater than or equal to 0. R is just always greater than or equal to 0. So this is our restriction for r. And now we want to talk about, okay, what can theta be? Okay, so here I'll put theta here. We know that we want theta to be bound by 2 numbers. And if I look at this circle here, I can kind of think about it a little bit like the unit circle, and we can still assign it some angles at each spot, right? So like this would be 0 radians, this would be pi over 2 radians, and this would be pi radians, and then 3 pi over 2 radians, and then we have 2 pi radians, and so on and so forth, all as we go around. So in this particular instance, we are looking for we're looking to create a circle that is starting down here and then goes all the way up to +2, passing through 0. So what that's really going to mean is that, I mean, instead of starting at 3 pi over 2, we really just want to start with negative pi over 2, have it pass through 0, and then go all the way up to pi over 2. So we want theta to be able to go around up to there. So theta is going to be bound from below by negative pi over 2 and can be no greater than pi over 2. The reason that I say negative pi over 2 and not working with that 3 pi over 2 is because I just want to make sure that it passes through 0 and then goes up to pi over 2. If we were to start at 3 pi over 2, then we would be going up to like 5 pi over 2 up here. It just keeps everything really nice and consistent. And again, make sure that we pass it through 0 instead of 2 pi or doing something weird like that. But anyway, our goal here was to get a domain that describes the points r, or not the points, but like the information r and theta that we want. So we have bounds for both of these. So now we want everything r and theta such that r is between 0 and 2, and theta is between negative pi over 2 and pi over 2. That's really pretty much all there is to it. So that has converted this region into polar coordinates. Let's do another one with the polar coordinates before we move on to the other two things that we're really concerned about today. So in this example, we have that our region D is equal to, I'll do this on a new line, the points x, y, such that we have x less than or equal to 0, y less than or equal to 0. And then we also have that 9 is less than or equal to x squared plus y squared, which is less than or equal to 16. Okay, so once again, I'm going to go ahead and start by drawing my region here. So looking at this right here, x squared plus y squared greater than or equal to 9, that's going to give me a circle of radius 3, and I want to be on the outside of that circle, so we'll call this 3. Okay, but we also want it to be inside of a circle of, this will be radius 4 is what that 16 would correspond to. So 4, 4, negative 4, and then negative 4 down here. So it'll look something kind of like this. So we want it to be between these two circles. And then we're also told that we want x and y to be less than or equal to 0. So I'm going to be looking at this area down here because this is where x is less than 0 and y is less than 0. So it's going to be this area right there. Great. Okay. So again, we want to create a domain that has information about r and theta that follows these restrictions right here. So let's go ahead and start with r. Once again, r squared is equal to x squared and y squared. So r squared has to be between 9 and 16, which means that r squared has to be between 3, or r has to be between 3 and 4. Okay, so that's our first restriction right there. Now we need to come up with something for theta. And we can apply the same logic that we did earlier, where we're, we still have the 0, the pi over 2, and then pi is right here, and then 3 pi over 2 is right here, or we can say negative pi over 2. But I think in this case, we're going to want that 3 pi over 2. So we really just want the region that sits between pi and then goes down to 3 pi over 2, which means that we want theta to be kind of along there. So theta has to range between pi and 3 pi over 2. And in this case, it really would be, we really do want to end at 3 pi over 2 instead of saying negative pi over 2, because if we were to say pi to negative pi over 2, we would suddenly be going kind of like, talking about maybe more like this chunk here instead of this chunk here. So you can kind of think about it as giving you maybe a sense of direction, or like which way you're moving, in that you're starting at pi and then going to the larger number, 3 pi over 2. So we're looking at this right here. So our domain, now we have adjusted this to be have restrictions for r and theta, and we have that r has to be less than or equal to or greater than or equal to 3 and less than or equal to 4. And theta has to be between pi and 3 pi over 2, just like so. And yeah, that's pretty much all there is to it for the polar coordinates. All right, so now we're ready to start talking about cylindrical and spherical coordinates. And I'm just going to show you what each of these look like, and then we'll talk about a couple of examples for each of them. So the first one, cylindrical coordinates, is really nice because it's quite similar to polar coordinates, except we're just adding kind of an extra dimension to it. So in cylindrical coordinates, what this is saying is that, okay, well, we have our x, y, z axes like so. Just to be clear on how I'm drawing my axes, previously I was drawing them with the x pointed this direction and the y pointed this direction and z pointed this way. But now the way that we're thinking about it, just with the way that we've been able to use them the most in the last couple of videos, it's been really helpful to kind of have a rotated version of the axes. So I haven't really flipped what x and y are. You can just think about it as, okay, I've taken the x-axis and now I've rotated everything this way. So now the positive y-axis points backwards and the positive x-axis points to the right. But anyway, okay, all of that aside, this just makes drawing the pictures a lot easier. There's really no particular reason other than that to do this. So when we're thinking about a point in the x, y, z space, say it's like out here, okay. Okay. And this point is, you can think about it as hovering above the XY axis. So it's got kind of like a shadow that comes down here. And then maybe it's like if you project it downward, there's a point right there on the XY axis or the XY plane. And then there's a distance there between this point that is now on the XY plane and the origin. And the way that we work with cylindrical coordinates is to say, okay, what we're going to do is actually say we're going to squish this point down to the XY plane. So floop, just like that. And then we're going to say, okay, well, there's this radius right here. Okay, call that R. Just like we do with polar coordinates. Everything now we can do the same thing as we had with polar coordinates. So we have R and we have theta, just like that. Okay, and so now everything is the same as polar coordinates. We get x, our x coordinate is equal to R cosine of theta. Y is equal to R sine of theta. We have that R squared is equal to x squared plus y squared. And we have that theta is equal to the inverse tangent of x over y. Great. Everything's the same so far. The only thing is, how do we deal with, okay, well, this obviously, it doesn't do us any good to just squish it down to the plane and leave it there. We still need the notion of height. Well, maybe this is a little bit silly, but the way that I think about it is, okay, well, we can just take like, almost treat it like a little elevator and have it ride back up to, you know, the top here to have a certain height z. Okay. And really all we're doing is saying, okay, we still have our polar coordinates and we're just letting z be equal to z. Okay. So we've kind of squished it down to the XY plane, do polar coordinates, and then treat z as though we're just kind of like moving it up and down with a little elevator or something like that. And that gives us our information about the height. So that's pretty much all there is to cylindrical coordinates. All right, spherical coordinates are a little bit more involved, but not. Sometimes they look a little bit scary, but I promise that they're not. Okay, so let's draw our coordinate system again. A little bit larger because there's gonna be a few extra details to these drawings. So this is still our x-axis, our y-axis, and our z-axis. And suppose that we have our points out here. Okay. So once again, we still have this notion of being able to take our point and project it down to our XY plane. Okay. And we're still able to say, okay, we can kind of dot this backwards to the origin. But instead of worrying too much about this length here, the only part of this information we're going to worry about is going to be our angle theta, okay? And so at this point, okay, that gives us information like this way and that way, but it doesn't tell us how far away, like how far out we're going and stuff like that. And the way that we're going to measure this is to use the radius that starts at the point that we originally had and goes back to the origin, like so. And this radius right here is called rho. Okay, so it's kind of like our new piece of information. And then finally, we need information about how much rho is going to swing up and down. And that's created by this angle here between the arm rho and the z-axis there. And this is going to be the angle phi. Okay. Or sometimes you'll see it drawn like a little U with an extra curly. So anyway, we can put all this information together to get our x, y, and z, or to be able to convert the x, y, and z coordinates over to this. And what you wind up with out of this is going to be an ordered triple rho, theta, and then phi. And I guess I should have mentioned up here, you get r, theta, and z instead of x, y, z. And the way that we do this is x is going to be equal to rho sine of phi, where phi is this angle right here, and then times cosine of theta. And the cosine of theta comes from the same place that it did up here, because it's really just this angle down here. And then the rho sine of phi comes from the fact that, okay, this leg right here is the same thing as this leg up here. And this leg up here is sine of phi times the length of that leg there, because you can think about this as being a right triangle. So this leg here, this guy right here kind of corresponds to like the r that we had up here, and you derive that from this leg times sine of that angle there. So similarly, y is rho sine of phi, and then sine of theta, because again, same idea as right here. We're working with this angle down here in the xy plane. And then now z is equal to rho cosine of phi, because z is just this piece here, right? So this is the adjacent leg for this angle here. So sine or cosine of this angle times our hypotenuse rho would give you the height there. Okay. So, but anyway, I mean, like if you just want to memorize these, you can, but just so you're aware of where they all come from, this is kind of the idea. And I mean, like the main thing here is that you really just have this arm here that has length rho that's kind of swinging around in space. And then you're able to describe its exact location in space by saying, okay, how far did we move down from the z-axis, and how far left and right did we go on the xy plane? And that's what's given by that angle theta. So up and down is controlled by phi or phi, or however you want to say it. And then left and right is controlled by theta. And then how far away from the origin is controlled by rho. And that's just kind of the idea of spherical coordinates. And if we want to be able to kind of go, actually get the spherical coordinates, I guess you say that rho is equal to, or rho squared is equal to x squared plus y squared plus z squared, because it's really just the hypotenuse of, well, all of the x, y, z information put together. Theta is still just equal to inverse tangent of x. I keep putting x over y. It should be y over x. I am so sorry. Y over x. Y over x, just like so. And then phi is equal to inverse cosine of z divided by square root of x squared plus y squared plus z squared. And that just really comes from this guy right here, because rho is equal to square root of all that. So, okay. So I guess that probably kind of sounds like a lot, but the big thing is to just kind of keep these equations in mind and be able to use them for substitutions. And again, this is kind of like the geometry behind it, but you can kind of wrestle with that as we move forward. So, okay, let's go ahead and work through some examples here. So in our first example, we are going to write a domain D equal to X, Y, Z, such that, actually we're going to say that this is in the first octant. And this is going to be such that x squared plus y squared is less than or equal to 25. Okay, so let's try to sketch this region to the best of our ability. Okay, so we have z-axis, x-axis, y-axis. Okay, so first and foremost, we're going to look at this guy right here. X squared plus y squared less than or equal to 25. That means we're looking at circles along that are kind of parallel to the xy plane that always have radius 5. Okay. It's really just a cylinder, honestly. So we'll call this 5. So I will attempt to draw a circle here. Okay. And then a cylinder, so it's going to have straight vertical sides. And I can attempt to draw some cross sections. All right. You get the idea. That's a cylinder. Now, since we're working in the first octant, that means that the part that we are really interested in is going to be this segment right here where everything is, I'm going to use a brighter color. Everything is going to be, I will do orange. Everything will be positive, like so. Okay. So Z is positive. X is positive, Y is positive, all that. That's kind of like this part right in here. And I should probably label my axes. So this is Z, X, Y. Okay. So we're going to do cylindrical coordinates. Oops. In cylindrical coordinates. And cylindrical coordinates is really nice for this type of setup here because, I mean, frankly, we have a cylinder, right? It's kind of in the name. And generally speaking, cylindrical coordinates are used to kind of describe things in terms of cylinders, like where they would be on a cylinder. So anytime that we have a cylinder, it's a great opportunity to use cylindrical coordinates. Okay, so when we're working with cylindrical coordinates, we know that r squared is equal to x squared plus y squared. So that's what this guy right here is going to become. So we know that r squared is less than or equal to 25, which means that 0 is less than or equal to r less than or equal to 5, because once again, r is always positive. Great. Okay. And then also, I'm gonna put it down here. What we're going for here is we need r, theta, z, and restrictions on each one of these. Okay. So now we need to talk about what we want theta to be. So we can actually apply the same idea here that we did in polar coordinates, and we're going to go along our xy plane here and label what each of the angles are in each direction. So like starting here in the positive x direction, that would be 0 radians. And then as we move up to the positive y-axis, it's just pi over 2. And then we have pi, and then we have 3 pi over 2, or we could call it negative pi over 2 if we want to, but we don't really need to this time. So we need something for theta. And this time we know that we want our radius to kind of like start here at 0 and then be able to swing around up to pi over 2. So we want theta to be able to start at 0 and go up to pi over 2. So that's what our restrictions for theta will be. And then finally, we want to look at z. And we note that since we are in the first octant, this means, well, x greater than or equal to 0, y greater than or equal to 0, and then finally z greater than or equal to 0. So this guy right here is going to be our restriction for z. So now we've completely described our domain in terms of r, theta, and z. I'm going to put all that in here. R is less than or equal or greater than or equal to 0, less than or equal to 5. Theta is between 0 and pi over 2. And then finally, z is greater than or equal to 0. So yeah, that's pretty much all there is to it. Again, same idea as working with polar coordinates. We just have this added thing of, well, whatever we did with z here also has to get tacked onto the end there. Great. Let's look at a spherical coordinates example. So in this one, we have d equal to x, y, z in the first octant. And this will be such that x squared plus y squared plus z squared is less than or equal to 16. Okay, let's look at this particular shape. So this one, I'm just going to really kind of draw the quarter of it. So we're looking at this is a sphere with radius 4. And we're looking at the first octant, which means we have x greater than or equal to 0, y greater than or equal to 0, and z greater than or equal to 0. Oops. And since we're going for this to be, I'll finish drawing the thing first. Okay, so our shape, I guess I will draw it in pink. It's going to look something kind of like this. Draw like a quarter of a sphere. This is going to be it right here. Okay. So our goal for this is to write our domain as having a rho, a theta, and a phi. So we need restrictions on each of these. So the very first thing we're going to note is that we need, so we're going to work with rho here. So rho is the part that it starts at the origin and it goes out to wherever our point's at. Okay, so like this would be rho right here. You can think about this little radius here as rho. And we know that rho squared is equal to x squared plus y squared plus z squared. So in this case, we know that rho squared has to be less than or equal to 16, which means that 0 has to be less than or equal to rho less than or equal to 4. Since rho plays a similar role as, like it's just a radius, it's the length of this arm right here, rho is always positive, once again. Same idea as r. Okay, so that's our restriction for rho. Now we want to work with theta. And remember that theta is, if we project our little point down onto the xy plane, it actually plays the exact same role as theta in cylindrical and polar coordinates. So it's this little thing right here. And it really just tells you how much of the xy plane we are going to take up. Okay, and here, in this case, we're going to be looking at, we can still apply this same process of 0, pi over 2, pi, and then 3 pi over 2 over here for our negative y-axis, okay? And we're allowing theta to start at 0 and go all the way up to pi over 2, okay? Because it's allowed to range from here all the way up to here. So 0 is less than or equal to theta, less than or equal to pi over 2. Great. Now for the little bit of the trickier part is working with phi. And remember that phi is this angle right here. It's how much we allow this arm here to swing up and down along the z-axis. So, it's allowed to start up here at 0. That's the upper part of the z-axis. And then it's allowed to go all the way down until z is negative, which this is going down to down here. This will be pi degrees. So it's actually allowed to range 180 or pi degrees, pi radians. It's allowed to range 180 degrees, starting at 0, going down to pi. There's no point in having it swing past that, because swinging in this direction can actually be controlled by moving theta around farther. So phi is always between 0 and pi. But in this particular case, we want it to stop when it hits the XY plane. And so stopping at that kind of halfway point, anywhere on the XY plane, gives us that phi is equal to, that would be pi over 2, because then it's sitting here at a 90-degree angle to the z-axis. So pi over 2, phi is equal to pi over 2 on the xy plane. And that's exactly where we're wanting to stop our sphere at, because we really just want the positive part of it. So in this case, we have that phi is allowed to start at 0, but it's only allowed to go as far as pi over 2. And that really gives us all the information we need to be able to do spherical coordinates. So rho was between 0 and 4. Theta is between 0 and pi over 2. And then finally, phi is between 0 and pi over 2 as well. Great. Okay. And again, one of the ideas behind working with spherical coordinates, it's in the name, is that you're trying to describe everything in terms of where it would be located on a sphere. So anytime you see something that maybe looks like a sphere, you're probably going to want to use spherical coordinates. Okay, I've got 2 more examples here, and they're pretty similar looking. So I kind of wanted to go over them because it kind of helps highlight, all right, when do you use spherical versus cylindrical coordinates? So in this first example, we have that d is equal to x, y, z, such that the square root of x squared plus y squared is less than or equal to z, and we want z to be less than or equal to 4. Okay. So in this one here, let's go ahead and draw our shape. If you kind of remember back to the identifying quadratic surfaces part of this, this is going to be a cone, and just the positive half of the cone. So we're looking at something kind of like this, where the height of this cone is at 4. Okay. And again, this is the z-axis, y-axis, and x-axis. Now, in this particular case, it's quite possible to go ahead and just do this with cylindrical coordinates. So I think that's really all we're going to do, because in this case, we do have kind of a notion of like we could fill in a radius here pretty easily, and we just have z. So let's go ahead and use cylindrical coordinates. A lot of times when you just have z like this as one of your restrictions, cylindrical coordinates are going to be your best bet. So when we're going for cylindrical coordinates, remember that our final desired point format is going to be r, theta, z, and we need to get information on each one of these. I mean, I guess z is pretty easy. Like, we're given that it has to be less than or equal to 4, but let's go ahead and start with r. So r, we can just substitute that in immediately. So we said that r squared was equal to x squared plus y squared, which means that, well, r has to be equal to the square root of x squared plus y squared. So then I know that r has to be less than or equal to z. Well, that's pretty easy. Okay, great. Well, we also know that it's greater than or equal to 0. So we know that z is less than or equal to 4, because that one's given to us. So the really big thing here is figuring out what theta has to be. So if we look at our graph with theta, again, we have the same idea of 0 is in the positive x direction, pi over 2 is in the positive y direction, and pi is in the negative x direction, and 3 pi over 2 is in the negative y direction. And theta, we can allow it to start at 0. And since we want an entire circle in our cone here, we have no restriction on like what segment of the cone that we want, aside from how tall we want it to be. We can really actually allow theta, we want theta to go all the way around, okay? So in this case, theta is going to start at 0 and then go all the way back around and end up at 2 pi. Just like so. So to describe our domain, we just want 0 less than or equal to r less than or equal to z. And we want z to be less than or equal to 4. And we want theta to be between 0 and 2 pi. Okay. That one really wasn't bad. That was pretty straightforward. Okay, our last example here, though, is really similar to that one, but we're going to have to take a different approach with it. So for this one, we have that our domain is equal to x, y, z. With square root of x squared plus y squared is less than or equal to z. And then we have x squared plus y squared plus z squared is less than or equal to 16 this time. Okay. So this right here is a sphere. So that should already be kind of letting you know that maybe we should be thinking about spherical coordinates. So let's kind of sketch this a little bit. I'm going to start by sketching that sphere, though, because that's containing our actual space, that cone there. So it's going to look something kind of like this. Okay, so radius 4. Okay, so this is just the sphere that is kind of containing the cone, putting the limit on it. Okay, and then the cone itself that we're interested in is going to be this guy right here. Notice that it does not go all the way up to 4 like our last cone did, because it's kind of running into this shape. Great, okay. And I think we're also including kind of like this top half. It's kind of an ice cream cone shape, I guess, where it's like all of that that's in there. Okay, so we need a way to be able to describe everything that's in here. And notice how everything, I mean, this is really just kind of like a segment of a sphere, okay? And so as a result, maybe the best way to think about this is to use spherical coordinates, okay? And just as like I mean, this isn't always the case, but a lot of times when you see a z squared, it's kind of a hint that maybe you want to use spherical coordinates. It's definitely a hint that you want to use spherical coordinates when you see everything you need to do a sphere. So that's what we're going to do. In order to get spherical coordinates, remember that our goal here is to get, we need points that are in the form of a rho, a theta, and a phi. Okay, so we need rules for each of these 3. Perhaps the easiest one to get in this is going to be rho. So rho is really just kind of like, once again, it's that arm that describes all the points. It's kind of like the radius from the point back to the origin. And in this case, we actually have, I mean, this guy right here is really just rho squared. So we know that rho squared is less than or equal to 16, which means that 0 is less than or equal to rho less than or equal to 4. So that one's pretty easy. Theta is also actually going to be quite easy because when we're looking at this, again, theta kind of comes down here, and we're looking at just like this little angle here between that arm and the x-axis. And so we can use our 0, pi over 2, basically our unit circle labeling on the xy plane, pi, 3 pi over 2. And we note that, okay, we want the entire cone all the way around. So we want theta to be able to go all the way around, okay? So it should go all the way around like that. So theta has to be between 0 and, well, 2 pi. Okay, because we want it to start at 0, come all the way back around. Because otherwise, this won't be able to go all the way around the cone. The trickiest part is really going to be to figure out what we want phi to be, this one right here. Because phi, remember, is this little angle right in there, okay, between the z-axis and rho. And it is allowed to vary overall between 0 and, well, down here, it can go all the way down to pi. But notice that in this case, we really don't want rho to exceed this portion of the cone. So we got to figure out what that angle is, because we want it to be able to go back and forth between z, which is 0, and then come all the way down to the edge of the cone. So there's a couple of different ways that we can approach this. So I'll show you the algebraic way, and then I'll show you kind of like the geometric reasoning type way that might be a little bit easier. There's one piece of information we haven't used yet. We have not used this. So that's what we're going to do next. We recall that x was equal to rho sine phi cosine theta. Y was equal to rho sine phi cosine theta, sine theta. And z is equal to rho cosine of phi. And we can put all of this information into here. So this means that the square root of rho squared sine phi squared cosine squared theta plus rho squared sine squared phi sine theta squared has to be less than or equal to rho cosine of phi. So I just took my identities that I had for x, y, and z and substituted them into this. Okay, literally all I'm doing is like maybe it's not immediately obvious that we're going to get information from phi out of this. I mean, I would not be able to tell by looking at this that I'm going to get told about phi. But I mean, like, it's information that I have, and it's information that I haven't done anything with yet. So we're just kind of going with it. All right. Well, we notice that we can factor out a rho squared sine squared phi, and then we're left with the cosine squared theta plus sine squared theta. I like to always be on the lookout for this identity right here because it makes things so much easier. So what this means is we have square root rho squared sine squared has to be less than or equal to rho cosine of phi. Oops, and that's a phi. Well, I can simplify that down a little bit. So I get rho sine of phi has to be less than or equal to rho cosine of phi. Great. So sine of phi less than or equal to cosine of phi. And maybe this is kind of a little bit of a tricky part here. I'm going to divide both sides by cosine, and I'm going to get tangent of phi has to be less than or equal to 1. Okay. So now at this point, I'm going to think about, okay, where on the unit circle is tangent less than 1? Well, that's only when your angle is less than pi over 4. So I know then that phi has to be less than or equal to pi over 4. I also know that I want that to be greater than or equal to 0, so I'm just going to tack that on there. And this would be my restriction for phi. So this is one way to do it. My point in doing it this way, I mean, this isn't the nicest way to do it, but my point in doing it this way is that you can always kind of brute force it, in that you can take, you don't know where you're going, that's totally okay. Just don't be afraid to take the information you have, take information you haven't used yet, squish them together and see what pops out, and maybe, you know, borrow some reasoning from some old classes, okay? It's totally okay. So there's a couple of different ways that you can approach this. Now, there is a much more elegant approach to this in that, I guess I'm going to kind of run out of space here. Get a new piece of paper. What we can do instead is say, or we can note that, well, that cone, it looks an awful lot like an absolute value function. This x squared plus y squared less than or equal to z looks like absolute value function. right? So if we look at it just in like, I don't know, we can look at it in the XZ plane. So we're just looking at this vertical cross section right here. It looks something kind of like that. Well, this is the line x is equal to z and x is equal to negative z. And this angle right here, well, I mean, that's phi, right? Because we're just looking at, well, this cross section. Well, it's pi over 4, okay? So that would be another way to look at it, that we're looking at, you know, I guess really more technically like this segment right here, but it can only go down to pi over 4, okay? Okay, so we're starting here and we're allowing it to go down to there. So obviously that was a lot easier, but I mean, like if you don't think that way, that's totally okay. I do this to point out to you, to show you that if you want to plug things in and see what shakes out, that is a completely valid method. I mean, this was a lot of times this will be my first attack at something because I know it'll always work. Anyway, we've got all of our pieces of information now. We have information about rho, we have information about theta, and we have information about phi. So we can put this all together to define our domain. Rho has to be between 0 and 4. Theta has to be between 0 and pi, or 2 pi, sorry, because we want it to go all the way around the circle. And then phi has to be between 0 and pi over 4. Okay. So yeah, that's pretty much all there is to that. Again, the big thing here is just remember, you can always think about this in a couple of different ways. We can think about it very geometrically, kind of like what we do with theta, and what we had our options with working with phi, or we can think about it strictly algebraically like we did with the rho squared, or in this alternative method to find phi here. So any way that you prefer to think about it works out great. Just make sure to, you know, justify your steps well and everything will be okay. So, but anyway, that's pretty much all there is to this video. Tune in next time when we're going to talk about how to use these to make integration a million times easier for certain shapes. I'll see you then.